Okay, so let's substitute. So let's call this relationship 2. Let's substitute the scale factors from 2 into equations 1, A and B. So what results now? Well, we first have to deal with the first term, mu times d square u by dy square. So to calculate d square u by dy square, we should use the chain rule. Yes? So d square u by dy square can be written as d dy times d dy tilde by dy of u can be directly replaced by u tilde uc. So far I've only replaced one of the dy derivatives by derivative with respect to y tilde. Okay. So now notice this uc of course is a constant, it will come out, and moreover the d dy of y tilde, if you rewrite this, is 1 over yc. So you get a uc by yc factor coming out of applying the first derivative. Y of you get a uc by y characteristic coming out, and then I can rewrite this derivative again as I have it here, and what I'm left with is dy tilde of u tilde. So this u by yc comes from the action of one derivative. I can now act the second derivative again by using the same chain rule, so you will just get a repetition of the factor. So you get uc by yc the whole square, and now the second derivative of u tilde by y tilde. So if I would recommend now in this and all the lectures to follow, since we are going to do derivations, that if any step you get stuck, please pause the video and you can try and work through the calculation at leisure and then resume it so that you're able to follow each step of the calculation. Alright, so let's take advantage of our online platform, which allows you to pause me and restart me at your pleasure. Alright, so carrying on, I hope you're all with me here. So you can see now that the chain rule allows us to derive this formally, but you see that the rule, we can do this much faster by recognizing that a simple way of substituting dimensionless variables is whenever you have the derivative, the result comes out to being simply putting in the constants and taking them before the derivative. So it would have been as good as saying d dy square simply means that I get a 1 by yc square factor on side, or by replacing y by y times yc and pulling out the yc in front of the derivative symbol. So that's a kind of a formal way of just doing it, but you can do it properly always with the chain rule. Okay, so now doing the same throughout the equation, the other terms are simple. We have the following relationship now. So mu viscosity uc square over yc square and d square u tilde by dy tilde square. Yes. So this is a factor of constants, although we are yet to determine or yet to specify what u characteristic and y characteristic is. And this is simply minus delta p over L. Alright, and the velocity boundary condition becomes u times u characteristic is equal to the slip velocity applied at, and even should put it at the location, I should non-dimensionalize the boundaries as well, at y times yc is equal to h. Sorry, I missed the tildes. Yes. Okay, so this is my equation right now, the governing equation and boundary condition. Okay, now what I'm going to do is I'm going to combine these terms so essentially the next step involves identifying one term which is essential to me. So this is now where we start to start to make comments about the governing physics or the physics of the problem. So you might ask, how can we make statements about the physics of the problem before we solve the problem? Well, even though we do not know the exact velocity profile, we do have an idea of what the governing key forces are. In fact, that's inherent in the equation itself. So let's take our problem for example. So we know that what we're interested in is the pressure-driven flow in a microchannel. So what is driving the flow? That is question number one. We have two options. It could be driven by an applied pressure gradient, or it could be driven by the slip electro-osmotic slip velocity at the wall. The second question is, what is resisting the flow? Here it's unambiguous. The flow is being resisted by the viscosity of the fluid. If there was no viscosity, the fluid would not require any pressure drop or any other driving force. So the resistance is coming from the viscous forces, and the viscous forces is this term. So clearly, regardless of whether the pressure gradient, how important the pressure gradient is relative to electro-osmotic effects, one effect that is certainly crucial to the description of the problem is the viscous forces. So I'm going to ensure that this term is retained in the equation always by making the non-dimensional term before it simply unity. In other words, I just take this term to the other side, or I divide throughout by the group that multiplies my viscous terms. Okay, so I can say multiplying, let me call this 3a here and 3b. So multiplying 3a by the inverse, yc square upon mu uc square. And similarly, I will multiply 3b with, now remember in this case it's trivial, clearly we need to specify the velocity to the boundary, so we just multiply throughout by u tilde. And similarly the y, we can just take yc to the other side. But when there are different terms, that's when the question arises. Okay, so what do we get? Also, now let us drop the tilde. Why? This is just so that it's easier for me to write the equations. But we will remember that the variables u and y are now dimensionless. So what do we get? So now what I have is d square u by dy square equals minus of delta p over L times yc square upon mu times uc square. Oh, sorry. Yes, I made a mistake here. There is no uc square. Yes, that was a silly mistake. There's only uc. There is no square sitting there. Let's see where I made the mistake. So you would realize that there's a mistake here because clearly my original equation had units of velocity over length square, and this term has to have similar units. I cannot have this extra uc here at the bottom. That comes out from here as well. You can see that there's a velocity upon a length square times viscosity. So having u square here made no sense. The reason I made a mistake is when I looked at the factor coming from the d dy, it was only 1 over yc. The uc came out of the u that was being differentiated, and there was only one u. So clearly this should be uc upon yc square, and there is no square here. Alright. Okay, so this makes sense now. Yes, so this entire term is non-dimensional as a collective. Each individual element of this term has dimensions, but taken together is non-dimensional, and that makes, and you can check this out, that the units cancel out, and that makes sense because my left-hand side term by definition is non-dimensional. And the non-dimensional boundary condition is u is equal to vs upon u characteristic. So this is another non-dimensional group at y is equal to h upon y characteristic, another non-dimensional. So this is equation 4. Okay. So now that we have written the equations in non-dimensional form, we are now in a position to specify what the characteristic scales are. So we are now at the step of choosing characteristic scales. UC and YC. Okay, so how do we do this? Well, remember now that we have already made one statement about the physics of the problem, that is that the viscous terms play the role of retarding the flow. Now when we choose the other scales, we are called to make another statement of the problem about what is driving the flow, or what is the key physics that leads to a non-zero velocity. So that means we have to make a choice between setting a velocity scale based on the pressure gradient, or choosing a velocity scale based on the electro-osmotic slip velocity. Before that, let's make the obvious choice for the length scale. So you see that we have a group here, h by y characteristic, and if we choose y characteristic to be h, then y becomes 1. The meaning of that is we are saying that our flow phenomena of interest is going to happen at scales of capital H, which is across the channel. In other words, what we're interested in is in the overall flow through the channel, rather than flow in any small region of the channel with a length smaller than h. Okay, so we'll first, so broadly speaking, what I've just said can be written as the fact that to choose characteristic scales, we want to set certain non-dimensional, I'll abbreviate here, non-dimensional groups to unity. So set which groups? On all the groups, of course, those which must be retained. So basically the terms in the equation that we believe are essential to retain, or that drive the physics, those are the ones that we should set to unity. In other words, remember that the coefficient in front of this viscous term is 1. So in order to balance it, I need to have another term of order 1. Similarly, this length, y is expected to, as a term in front of it, 1. So the other term should also be 1 to balance it. If h is extremely small, it doesn't make sense. I mean, if h by yc is very small, it won't make sense. Anyway, so this choice is obvious. So first we will say that yc is equal to h. Alright, and then how do we choose the velocity scale? So this is now the crucial part. We can either say that the velocity scale is given by Vs, in which case uc is Vs and the velocity is 1 at the wall. This would be equivalent to saying that the flow is being driven by the electro-osmotic velocity, so that its magnitude should be Vs. On the other hand, and this is the case that we are going to look at today, or look at now, let us say that the primary flow is being driven by the pressure gradient, and what I'm interested in knowing is how does a small electric field or a small electro-osmotic effect modify the flow profile. In such a case, I know beforehand, or at least the problem I'm interested in solving is one where the electro-osmotic effect is weak. In that case, the primary driver of the flow is the pressure gradient. And for such a problem, or the problem in this limit where the pressure gradient is dominating, I should set this term here involving the pressure gradient to unity. Because then what that means is that the pressure gradient is balancing the viscous stresses inside the fluid. And that is what is creating a steady flow. So I'm going to say because the pressure gradient drives the flow, I'm going to set this term to 1. So delta P over L times so now y characteristic is already h, so I can replace that. H square by mu uc is equal to 1, or u characteristic is now simply delta P over L h squared by mu. So you see, I found my characteristic velocity scale under the assumption that pressure gradient drives the flow. Okay, so let's call this phi. So then the non-dimensional equations become by dy square is now equal to 1 minus 1. Yes, because I have chosen UC such that this is 1. And the boundary conditions are, now U was Vs by UC. So U is Vs by UC means it's multiplied by yes, length times viscosity upon delta P times the height of the channel squared at, of course, y is equal to 0 comma 1. Okay, so now you see that we are almost exactly where we want to be. This group is a non-dimensional group which we will call pi. Oh, sorry, not this group, the group involving Vs. So the entire group so this group here is just the velocity scale. It has units of meter per second, or sorry, second per meter, because it's 1 over UC, and that multiplied the electro-osmotic slip velocity will be non-dimensional. So this entire group is non-dimensional. Let's call it pi, and this pi, which is a dimensionless parameter now, is what is going to give us the relative magnitude or how important the electro-osmotic flow is. So it gives me the relative importance of electro-osmotic slip, relative, of course, to the pressure gradient driving flow. Why do I say this? Well, because if I now say that pi is much less than 1, then I can solve a simplified problem with u equal to 0 at y equal to 0 comma 1, and this is simply pure pressure driven flow with a parabolic velocity profile. This is the problem that you would have solved previously. So it's flow where one completely neglects this electro-osmotic flow. So now you could have said, yes, I could have come right in the beginning and said, I'm just going to drop Vs and got the same problem. However, then I would not have been able to give you a condition for how small is small for Vs, for the slip velocity. But now you see, after scaling, I can. So pi must be less than 1. This means that if Vs is much less than, so from pi less than 1, which this is pi, if I take it to the other side, if Vs is much less than delta P h squared over L mu, right? Then this slip, electro-osmotic, may be neglected. So this is the condition that we have obtained purely from scaling. It's possible that if you had, of course, solved the full problem and then varied delta P and varied Vs and so on and compared these solutions, you could have arrived at some condition. But even then, the dependencies on L, mu and h square would require you to do separate calculations by varying delta P, then varying h, then varying L, then varying mu and so on. Whereas the scaling analysis has given us this relationship directly. Moreover, it shows us that the relative importance of the slip velocity basically grows, or rather, let's say that the relative importance of slip velocity it becomes smaller and smaller if the height of the channel becomes larger and larger. So you see, let's assume that I keep now Vs constant. That means my electric field driving the problem is fixed, and the electrical properties and the viscosity of the fluid here is also fixed. In that case, this term is fixed, and what is free is the height of the channel. So what you can see here is that if the height or the width of my channel gets larger, that means I go from quote unquote nominally microchannel to some macroscopic channel, then I can completely neglect electro-osmotic effects. This is why we don't bother about such charge-induced velocities, even if we have electric fields, in large pipes. But what is large? Well, large is exactly what it obtained from this condition. So if I fix Vs, I can then get an equation for a limit on H such that I can neglect the electro-osmotic effects directly from this inequality. Similarly, I can see what pressure gradient I need to apply before I can neglect the electro-osmotic slip, or how long should my channel be. So here you can see if the channel becomes very long, then again it seems to suggest that that the electro-osmotic slip may start to become important, because this term will become small if the channel becomes long, and so on. Okay, so this is now already one fruitful result from scaling. Another fruitful result which would happen even if we hadn't done order 1 scaling is simply that I have now reduced the number of parameters to 1. So if you look at the governing equation, you see that earlier I had separately the parameters of viscosity, delta P, etc. Now I just have one parameter in the equation, pi. Right? Pi is the only parameter. And so I know that I will get the same solution if I increase the channel length, or if I keep the channel length fixed and increase delta P, or if I increase H, but only as a square root as I would increase L, and so on. So we have simplified purely the complexity of the problem by reducing the number of parameters. This results always from non-dimensionalization, and it's something you could have figured out using the so-called Buckingham-Pai's theorem of the non-dimensional analysis. We have done something more than that, because rather than just choosing groups of parameters that become non-dimensional, we have chosen groups in such a way that we have ensured that the order of the key terms remains order 1, and that has allowed us to then make statements about which terms can be neglected based on the surviving non-dimensional group. Now, what I just said will become even clearer if we consider what would happen if I make the wrong choice of characteristic scale. So that will just illuminate the whole exercise. So let's say, suppose I chose the quote-unquote wrong, because we will see in what sense what we're going to do is wrong and in what sense what we had just done is right. Suppose I choose the wrong UC. That means if I, coming back here, where was I? Yes, coming back here, where I have to choose between which of these terms, the one involving delta P or the one involving Vs, to make unity and set new characteristic. Let's say that even though I knew that I was interested in a situation where the pressure gradient effects dominate, yet without realizing the importance of order 1 scaling, I simply said, hey look, this has Vs over UC, it would be nice to have U equal to 1 at the boundary, so I'll choose UC equal to Vs. Yes, suppose if I thought that it's okay, I can non-dimensionalize UC any way I want, anyway I'll get only one parameter in the problem, and that's all I'm interested in. Then I could just set UC equal to Vs and feel that no harm would be done. So let's say I chose the wrong UC, that is, I'll set UC equal to Vs. Okay, then what happens to the equations? You see, then I have to substitute, pardon the pun, and then I have to substitute U characteristic equal to Vs in this term, whereas U would just be 1 at the bottom. So this will be delta P over L squared by mu Vs. minus delta P over L yes, but this is nothing but 1 over the old pi that I have, right? Yes. Right, or let's recite it again, 1 over pi, well, in fact I can take it to the other side, so let's say pi d square u by dy square. So just taking pi to the other side is equal to 1 and u is equal to 1 at y equal to bottom wall and the top wall. Okay. So you see again, even though we chose a different scale, we still got the same non-dimensional parameter and there's only one parameter. So you might think, okay, all is well, but actually it isn't, because you see now if we want to think about how to simplify the problem, and then I say that the pressure gradient dominates, which means if I say that pi is much less than 1, then what simplification would I get from this equation? You'll see if I ignore pi, if I take pi to be very small, I'll get the absurd result that 0 is equal to 1. Right? This makes no sense. And so I reached a sort of contradiction. You can see this even here, even if I don't set pi to 0, just so that it's very small. Remember that our order of magnitude scaling implies that this term has a maximum value of order 1. It cannot be greater than 1, because this is what we mean when we say order 1 scaling. We would interpret it this way. So if this term is order 1 and this is extremely small, it means this whole term is very small. So how can a very small term balance a term which is 1 here? This statement itself makes no sense, and this is the ultimate version of that, 0 equal to 1, which is an absurdity. So clearly, choosing the wrong scale has led to a contradictory idea. The reason is that this condition, pi much less than 1, contradicts the physical statement we implicitly made when we made UC equal to Vs. Because here we said the velocity is determined by electro-osmotic flow. Whereas here when we came, we said, hey look, pi is small, which is saying that the pressure gradient is dominating the flow. Yes, remember, pi is inverse 1 over the pressure gradient. So this makes no sense. Instead, if we want to say this, that UC is equal to Vs, it should correspond to the condition that pi is much greater than 1. So I'm only justified in making this statement UC is equal to Vs. So let's just do that here. This only makes sense, only works if we had the problem where pi was greater than 1 or the electro-osmotic flow is dominant. Right? Similarly, this condition again would tell us how large Vh should be or how small delta P should be for this to hold. But if this holds, and if I came into the problem saying, hey look, I'm mainly interested in electro-osmotic flow and the pressure gradient is a small effect, then I know that pi is much greater than 1. Then it would have made sense for me to choose UC equal to Vs. And in that case, my equation, remember now pi is much greater than 1, I would take pi to the other side and say d square u by dy square equal to 1 over pi, which means that if pi is much greater than 1, it implies that I could get a simple solution. It's basically 0, right, which would imply that u is equal to, if I just solve it now, where a and b are some constants, and then the boundary conditions of course are that u is equal to 1 at y is equal to 0, 1, which if I apply here will tell me that a is 0 and b is 1. And so I would get u equal to 1 as a solution for pi much greater than 1. Which basically means that my velocity profile, if it was electro-osmotic flow dominated, would just be a flat line. Right? Because at the walls I would be driving it with Vs. And everywhere this velocity is Vs throughout the domain. Because I'm saying that the pressure gradient has no effect and the viscous forces don't really play a role if there is no shear, if there is no way to retard the flow. So everything just moves with Vs. Or in other words, the diffusion of viscosity during viscous forces just allow the velocity at the wall to propagate throughout the fluid, and under steady conditions the whole fluid will move with the velocity of the wall. In fact, this sort of flat velocity profile is what people observe in experiments that are purely electro-osmotic flow driven. Whereas we know for the pressure gradient problem, you will get a parabolic velocity profile. So in contrast, so this is the electro-osmotic flow version, whereas in contrast in pressure gradient flow, this is what you will get. This is delta P driven, or this is when pi is much less than 1, and this is when pi is much greater than 1. The fact that this is a parabola, of course, we know, we have already got the equation here. Yes, this problem. E square v by u is minus 1 and y is equal to 0 at the walls. If you solve this equation, you will get an equation for a parabola. Okay, so now we've seen that that if we enter the problem with some understanding of the physics, we should choose the scales which are corresponding to that understanding. In case we don't choose the right scales, then when we come to taking limits, we will realize, or the problem itself tells us that something has gone wrong. In that sense, scaling analysis is also forgiving. It guards against inadvertent mistakes and forces us to revisit our understanding about the problem and correct it. So that's a nice feature of scaling.